Hello there and welcome back to this video series on control systems. In the previous video, we have seen some topics which are useful for principle of argument. We defined what are open loop poles, closed loop poles, what we mean by encircled, enclosed, and how to count the number of encirclements and such topics. In this video, we will build on that. And after watching this video, you will perhaps be able to specify what is Nyquist path, what is Nyquist plot, path and plot. Carefully make the distinction and specify how Nyquist criterion is applied in the case of control systems. We will begin by considering what we call Nyquist path. Okay, carefully note Nyquist path. This Nyquist path is one particular choice of the gamma S path as shown below. This path encompasses the complete right hand side of imaginary axis. This imaginary axis divides the whole plane into two halves. One is left half, one is right half. We are interested in this right half because if any even one root lies on the right half of the S-plane, the system is unstable. So we choose either this or this as the gamma S path and we call it Nyquist path. We use this particular choice consisting of one big semicircle and one small semicircle in case where the transfer function has a pole at origin, that is, if there is an S term in the denominator. When this S term is there in the denominator, the delta S involves something divided by 0, which we don't want. So we use a small circle just small enough to avoid the 0 at the origin. Thus we say this radius tends to 0. It's not equal to 0 but tends to 0. Similarly, this big semicircle has to encompass the entire right hand side of the imaginary axis. So we say this big R tends to infinity. So corresponding to each point on this Nyquist path, that is, we consider S1, S2, S3, so on, maybe 1000 points on this Nyquist path, either this or this. Corresponding to each point, you compute what is delta S1, delta S2 and so on, and then you plot it on another graph sheet. That graph sheet is what we call delta S plane. In this plane, you count how many times this curve is encircling the origin. Let that be n. Let p be the number of poles of this delta S that are encircled by the Nyquist path. Okay. Now the trick is we subtract 1 from every point here. So from here it moves 1 unit to the left. From here it moves 1 unit to the left and so on. That is, the whole graph moves 1 unit to the left. When it moves, see what happens. When it moves, every point related to the curve moves, and so does the origin also has to move. Okay. Now we count encirclements about -1 plus j0. Okay, because the entire curve moves to the left by 1 unit. We'll show that once again. The point of interest now is origin for delta S, and you move the entire curve 1 unit to the left, and now the point of interest is -1 plus j0. So with this understanding, we can specify the Nyquist criterion as given in the next slide. If n is the number of encirclements of Fs, we are now calling Fs, we are not calling delta S because we subtracted 1 from every point. So delta S minus 1 is Fs. We'll call it Fs path. This Fs path is what we call Nyquist plot. Okay. So we count how many times this Fs path n circles minus 1 plus j0, and p is the number of poles of Fs encircled by Nyquist path, then the number of roots of characteristic equation encircled by the Nyquist path is given by z is equal to n plus p. Okay, we see that z should be 0 for stability. Thus, in summary, we say that the principle of argument as applicable to the stability of control systems we have seen that there is one particular choice of the S-plane path, which we call Nyquist path, which consists of a big semicircle and small semicircle, or just the big semicircle, and -1, 0, or as we call it -1 plus j0. 0 is the imaginary part, is now the point of interest, and encirclements about this point are counted. We will see how to apply this in a couple of problems in the subsequent video. I think that's all we have for now. Have a great day.